I wanted to thank, first of all of you for coming today on this somewhat dreary day to hear me talk about climate change. I'm predicting that you'll hear some stuff you've maybe already heard, but you'll definitely hear some new stuff. And I'd also like to thank, in particular, Ed McCord for hosting me and taking me around the campus today, and for my lovely day at the museum, which was great for any nerd like me. So thanks a lot, and also to Mark Abbott for contributing to this series and for having me up, being a wonderful and very old colleague. So what I'm showing here in front of you is a picture from my research site. It's in the middle of the tropical Pacific. It's actually almost in the geometric center of the Pacific, which takes up half of our planet. We'll get back to that. But what you see here, these ugly-looking gray things, those are corals. Those used to be growing on reefs at this island centuries to thousands of years ago. And as was just noted, I'm going to use those to reconstruct climate patterns in this extremely remote place, far away from most human influences, but under the influence of climate change nonetheless. And we're going to look at what's occurred here, and that's going to strongly suggest that some trends are underway that we should consider in the future with respect to climate extremes. So climate is changing. I take that as a default statement. I'm not going to go through all the evidence for climate change in this talk. Rather, I'm going to take you to the cutting edge of climate change research and try to understand how we know what we know in this very remote place, what it tells us about the unprecedented nature of current climate change as told by corals, and about climate extremes. So I'm going to allow the rocks to talk for themselves today. I hope they speak to you, and hope that by the end of this talk you understand their power in addressing climate uncertainties and in speaking to folks like you who want to be more informed about this issue. So the question is, why is climate changing? This is the million-dollar question. Is it all due to human influence, or is it partly due to natural factors such as solar and volcanic variability? And that, of course, immediately derives a second question. What should we do about it if it's all our... This mic is very nonlinear, so pardon, it's not my voice. So what should we do about it? If it's really a problem that we are creating, then that implies that we should take action. And much of the climate skeptic community would have us believe that we have very little to do with the fact that climate is currently changing. So we're going to turn to the rocks. First, we're going to note that the IPCC, in its latest report, this is something you may likely know or have read about in the media, it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. And extremely likely means 95%, and that's an important number in science. That means that something that we act on as scientists, we believe is a scientific truth. That implies a warming in the future, as we ramp up CO2 emissions, of 1 to 5 degrees Celsius over the next 100 years. And that implies many regional impacts, some of which were mentioned, related to extreme storm events, sea level rise, temperature patterns, melting of glaciers in some regions, flooding in others. It's a problem that will likely touch every region of the world in somewhat in different ways. And so I put here this image of these heat-baked soil alluding to the drought that has been gripping with the western US over the recent past. And there's been a flurry of media activity, this one just from a couple days ago from the US News and World Reports, indicating that climate change may play a role in that drought. And it is exactly that kind of science, very much at the cutting edge, that I'm going to be talking about today with respect to understanding and putting into context current trends in climate and seeing how unusual they are. So the question is, how can we use these long records? The places where I work, and this is another picture from my research site, I hope you're getting the idea that this is a really nice place to work. Which is why I keep going back there, and we'll keep going back there for a very long time. But these kinds of sites allow us to use records of centuries and thousands of years long to understand and put into context the current trends that are occurring at these sites. So we're able to disentangle the role of natural variability at these sites from the role that carbon dioxide may be playing in changing climate at that site. And that is the key information that we can extract from long records that we cannot extract very often from short instrumental records of climate. So I'm going to take you, I promised, the middle of the Pacific. This is a picture of half of our planet, which the Pacific covers. And I wanted to show this because we're talking about a site in the middle of nowhere. In fact, my site is at the geographic center here, at the center of this box. And this is, again, far from most sources of human environmental contamination, but it is not too far to receive the impacts of global warming and carbon dioxide rising. I want to note in this image, while you're here and stuck in this big, beautiful ocean, that we have very few measurements of climate from this region of the world. You can go back 50 years, and you still have somewhat of a reasonable record. But if you go back even 70 years at this site, you'll be dealing with a handful of temperature estimates that are derived from opportunistic ships that take them, and many errors, and you're simply at a loss to explain and document the trends that are occurring in this area very well. So that's why we turn to these longer records. And this site is also important because it's home to a climate phenomenon which is extremely important. And it's called the El Niño Southern Oscillation, and it's a natural climate cycle, so it's not caused by global warming. And it causes temperatures in the tropical Pacific to go up and down every 2 to 7 years by quite a lot. So the average El Niño may be 3 degrees Celsius, and then the La Niña, which is the cool phase, will be 3 degrees cooler. So you have this warming and cooling every couple years. It's born in the middle of the tropical Pacific, where I do my research work. And the important thing is for climate is that it causes changes in the temperature and precipitation patterns all around the globe. Okay? It's really nowhere you can go that you don't see this climate cycle written into the climate record. And so it has a profound effect, especially on rainfall, and especially on California rainfall. So it's relevant even to the most pressing issues that we face today. The question that I'm going to pose for my research, which has been extremely hard to answer, it has taken me 20 years, and to refine my answer will take me another 20 years. That's good, because I really like my job. But is this climate cycle changing in response to rising CO2 concentrations? And this is a $1 million question because of its global reach in the climate system. So if it's changing in its extremes, then those extremes are going to be translated into greater extremes in areas that are impacted by this very large-scale, very powerful climate cycle. So that's an important question. And we simply don't have records from this key area in the tropical Pacific to answer that question from instruments alone. So of course we get to go scuba diving in the tropical Pacific and try to answer this question, which is pretty nice. This is a picture from one of the reefs that I work at in this area. These reefs are incredibly beautiful. They've been there for thousands and thousands of years, and we're able to go and extract coral from these records. And so this is me there doing my Indiana Jones impersonation with my hydraulic drill, looking pretty beastly, if I may say so. And this is extracting a coral core that's going to take me back about 100 years. So with this core, I'm going to be able to understand how the instrumental record of climate is translated into the rock chemistry. And I'm going to use this very important piece of coral record to calibrate how I would read much older corals back in time. So while this doesn't predate the instrumental record, most of the records that I show you will very much predate the instrumental record of climate. This is maybe the most fun part, but the real core of the science comes when you look at rocks like this. So this is a fossil coral that's been deposited on a beach at one of my research sites, and this rock is about 500 years old. And I know that because I can use radioactive isotopes within the coral itself to measure the decay of uranium to thorium in this case, and I can measure those two parent-daughter isotopes extremely precisely, and I can get an age of plus or minus 1 year. So that's how well we can date these rocks. That's the only way I know when it grew. So this is about 500 years old. It's worth about 90 years of information in one chunk. And here's my drilling assistant very happily using himself for scale with the largest core we've recovered from these land-based fossil corals. In this case, this record went from 1319 to 1410 ID. Now we are really predating the instrumental record. But we're able to use the analog of the modern day coral that I recovered to understand how to read the record from this fossil piece, which grew long, long ago. And so we could even play this game back 7,000 years ago. In my latest work, we found some corals. They look exactly the same as the ones that are 70 years old. It's extremely frustrating. So you go down there and you sample several tons of material. You have to bring it all back to Georgia Tech. You date it, and you figure out what you want to work with, because they all look the same. So some of these rocks that you see here are actually 7,000 years old. These are fossil corals that grew at this site way long ago. It's a pretty picture of my hydraulic drill, which is much heavier above water than it is in the water, incidentally. It's not made for land-based drilling, but again, super strong. So we want to figure out what the rocks say. That's what we need to understand. They're trying to tell us something about past climate, but first we need to learn their language. Turns out it's not that easy to learn their language. It's taken me the first part of my career to learn that language, and the second part to apply it, let's say. It's difficult, but we've actually cracked it, and we think we've cracked it very well, and I'll show you proof. So a little bit of geographic understanding of how this system works and how we are able to extract climate records from corals, how we make them talk about climate. They are situated in the middle of the Pacific. These are the 3 islands I work with, Palmyra, Fanning, and Christmas. They're all interchangeably beautiful, each of them distinct and lovely. And I'm showing them on a map of temperatures, the temperature warming that occurs during El Nino events. So that those warmer colors is not exactly the greatest color, but the yellow to reds are warming during El Nino events that occur. And the black contours that are circling those islands is actually indicating positive rainfall in that area that occurs during El Nino events. So to summarize, during El Nino events, my sites get warm and wet. And during La Nina events, the cool phase of this climate cycle, my sites get cool and dry. And the warm-wet translates into an isotope signal in the coral, which is extremely robust. I'm going to show you proof. You don't have to take my word for it. That is indicated by lower coral oxygen isotopes, and the reverse during La Ninas. We have higher coral oxygen isotopes during La Ninas in the cool and dry conditions. And this is a game that I didn't invent. Oxygen isotopes have been around for 70 years, but in terms of applying them to these corals, it's kind of been my lifelong pursuit thus far. So we take these corals back to Georgia Tech, and we analyze them on my mass spectrometer. This is a picture of my mass spectrometer. It is the bane of my existence. It blinks and I jump. It's that kind of relationship. And we feed it all day, every day, and it runs 24 hours a day, 7 days a week, hopefully all year, unless it's down. It's up right now, so knock on wood. And it measures the ratio of these isotopes I was talking about. It measures the ratio of oxygen 18 to oxygen 16 in my coral samples. And I'm holding a coral sample right there. There's some pictured on that screen, which is not facing us in this horribly staged photo. But what we do is we drill 1 millimeter down the coral core. And every 1 millimeter of coral growth is about 2 weeks of time reflected in that sample. That's how finely resolved these corals are. That's how fast they're growing. They're growing about 2 centimeters per year. So that's a lot faster than my kid. So what about their coral story? Can we trust it? And this is, again, a kind of, you can barely see the color differentiation, but it doesn't matter because there are 2 curves plotted on this plot. This plot goes back to 1886. It's covering the 20th century. It's the core that I recovered underwater by scuba. So it covers the entirety of the 20th century. What we can see here is that the coral isotopes in red very much reflect the instrumental temperatures for what they're worth in this period over the 20th century, indicated in black. So over the latter part of the 20th century, we know extremely well what happened. Over the earlier part, the corals are corroborating what we can amass from this data set of temperatures through this very sparsely observed period. So this tells us that the coral isotopes are actually a very good indicator of what's going on at this site. And these temperatures come from an average of the entire middle of the Pacific Ocean, not just my site, but an average of any available temperatures we can get. So the coral isotopes at this one small speck of an island in the middle of the ocean are actually reflecting climate over a very large portion of the middle of the Pacific Ocean. a place where the reach of temperature change is global. So this is a key place to put our finger on and measure the pulse of what's going on today and decide if it's changing. So we can look at different corals. That's part of what I've been doing, is listening to a lot of different corals and hearing their stories and seeing if they align. And so this is a plot over the much more recent past using a bunch of shorter cores. And I'm looking at the isotopic signal in the coral on the y-axis. And this is just 1970 to 2013 on the x-axis. And I have, I think, 4 corals on there in different colors. And in gray, that you can barely see, but trust me, it's plotted, is instrumental temperature at this region as measured by satellites, okay, which is actually our best record. Of course, it's very short. So this tells us that the corals are telling us much the same story. So if we pick up a coral from 1400 AD and we measure the same isotopic content of the coral from 1400 AD, we can get a quantitative indicator of temperature changes during that time. And if we do this enough, we can amass a record and understand how natural variations in the past compare to what's going on today. And this is where we're going. Oh, that's another pretty picture of my research site. That's a picture of us drilling a fossil coral. In the background, you can see not only a beautiful horizon, but my internal combustion engine water pump perched on a fossil coral about a foot from the water line, which subsequently fell in the water. That happens all the time. Yeah. Saltwater machines don't mix. The field work is tough. So after 15 years of work, again, trying to learn the language of the corals, trying to understand if different corals tell you a different story, trying to dot all my I's and cross all my T's, I'm going to show you a plot that is extremely powerful. It'll speak to you, and it contains 40,000 individual isotope measurements. I think that's probably a record in my field. Here it is. Are you overwhelmed, underwhelmed? Let me take you through it. It's 15 years of my life, after all. So what you're seeing here is a plot of climate in the middle of the Pacific Ocean from these very small coral atolls that I work in. Corals that I've picked up on the beach are the older ones, and the modern coral that I drilled underwater is the one to the furthest right, and it's going from 1000 AD to present, more or less. And this is raw data in black. So this is actually what came off of my mass spectrometer. And it goes up and down in the black. Up is El Nino, warming, that's natural. Down is La Nina, cooling, and it goes up and down, showing us that this has been an ever-present feature of the climate system over the last 1,000 years. That's not really climate news, we expect that, but it's really nice to see that there's such a rich variation in temperatures in this site. What you see in yellow is an average of 10 years of information to just show you by eye how the climate is evolving through time. And what leaps at you off this page is that there's a trend towards different coral chemistries at the very, very end, a trend towards warmer, wetter conditions that began in the 1970s at the site as locked into the chemistry of the coral skeleton itself. That's quite unusual in the context of the last millennium. I don't have a complete record. It'll take me the next 40 years of my life probably to get a complete record. So hopefully I'll be able to fill this, but it's very laborious work. Nonetheless, I think we have a powerful message here. We can say that in the records that we do have, the late 20th century trend is unprecedented, okay? Now, this may not be, at the time it was one of the first records published from this entire area. It's nice to see that we corroborate many other temperature records that span this time interval, showing us that the late 20th century trends are unprecedented. So that's nice to see. This site seems to be similar in that regard. Much of the rich pattern of variability that we see prior to that is still the subject of intensive study, I would say. The one other thing we tried to answer, of course, is El Nino changing? Is this natural climate cycle changing? You can't tell that by eye. You need to bring some statistics. But I will tell you that this record indicates no change between the earlier part of this record in terms of the variability of that black curve and the later part of this record or the 20th century part of this record. There's such a high degree of natural variability that we don't see a change in this powerful climate cycle looking at this time frame. So that just got me thinking, great, I have more NSF grants to write. Now I really want to go back in time. I want to go back the full extent to what I can 7,000 years ago. And of course, I can't do 7,000 years of data at monthly resolution because that would take many lifetimes of work, okay? So I only have like 7 years to get this stuff done. I started this project in 2005 that I'm about to show you. So we've been working in parallel in the last millennium in the 7,000 year project. Oh, this is another gratuitous shot of my research site. Very lovely. So what I'm going to show you now is not a plot of raw temperatures through time, but I'm going to show you the strength of the climate cycle through time. And we're going to talk about that because that's the key question we were trying to answer. And this was published in Science a couple years ago. And what you see now, the x-axis is very, very long from my perspective. It goes from 7,000 years ago to today. And what we're looking at, those different dots, the color of the dots are coming from 3 different islands, the islands that I study. One is Christmas, Fanning, and Palmyra, as indicated there. And we don't have full coverage through this interval. What you're looking at really represents about total 1,800 years of coral information at monthly resolution. So very partially covering this space, shall we say. But nonetheless, what comes out from this, when we did this compilation, what I'm indicating in the gray horizontal line at 1 on the y-axis, if you go to 1, I don't have a pointer, but if you look at that line, it's a gray line, it's marked 1988 to 1998. That is the level of power for this natural climate cycle over the late 20th century. Okay, that's what I chose as my benchmark for 1. If it falls below 1, that means it's weaker than the late 20th century. And if it goes above 1, that means it's stronger than the late 20th century. So to take the data set en masse, we see that, wow, there's some stuff weaker than today, and there's some stuff higher than today, and a lot of variability in between. So we fleshed out a large amount of space with up to 80% reductions in strength in this very powerful climate cycle. We haven't seen anything like that, of course, this century in the instrumental record. But what we see if we step back and squint is that most of these older sequences are indicating that the El Nino cycle was much weaker than today. Not all of them. There are sequences indicating that it was stronger for a short period, like that one in 1600. But most of them fall below that 1988 to 1998 line. I think I was very stunned when I saw that. I did not expect that at all. And yet still your eye has trouble discerning whether there's been a notable change in this climate system with this data because of the high level of variability. So we had to run some very sophisticated statistics I don't have time to go into right now, working with some people that are very smart. And we determined that there was a statistically significant increase in the activity of this natural climate cycle within the 20th century compared to this entire baseline of several, again, many hundreds of years of fossil coral data. Again, this is all just measuring the extremes that are locked in the coral isotopes coming off my mass spec. So this is the power of this kind of paleoclimate data. Looking at the past allows us to have an idea of what the future will bring. If we can link these kinds of trends to understand them dynamically through a physical lens, then we can actually infer that it's going to strengthen through time. My money would be that based on this data, we will be seeing an epoch of intense El Nino events in the near future. We haven't had one since 1997-98. I'm still waiting for that big one, but this data would indicate that that intensity has ticked up. So I just wanted to make a note about my participation in this crazy project, this TV show called The Years of Living Dangerously. If you want to know more about this work, you can go to that program and watch me bumble through interviews and try to tell my story on site. They were famous for asking me, you didn't bring any makeup? I'm like, no, I'm actually working here, people. I didn't have the right clothes, I didn't have the right makeup, I didn't say the right stuff, but take a look anyway, and you can see a real live scientist trying to tell her story in front of many cameras and lights and a lot of this. So it was fun. It was a really fun project. Okay, so another pretty picture. Okay, so the coral records show that the recent trend towards warmer weather conditions at this site and the intensification of this natural climate cycle is unprecedented in the range of the coral records that we have. implying it's outside the range of recent natural variability, strongly implying that there's a role for carbon dioxide in shaping these recent trends that the corals are recording. Okay, so now what? I want to take 5 minutes and just take you beyond this. And I'm going beyond my own chartered territory here. I have actually stopped most of my talks right where we just ended. But I want to take you further. So now what? What do? We see this evidence all over the planet emerging that the climate is changing and that these impacts are going to modify our existence in very important ways. What do we do? What do we do as individuals? What do we do as society? There are 4 options for mitigating climate change. We can all choose to adapt and just move inland and take what we get, but I don't think that's very attractive. So these are the options. We can use less energy. We can shift to low carbon energy or more low carbon energy. We can take carbon dioxide out of the sky, or we can geoengineer our way out of this and modify our planet's energy balance. If that sounds scary, it probably is, the last one. So those are the only ways to get ourselves out of this problem. I'm going to focus on 2 today because I have an example of these 2 that I'd like to bring to you that I hope is an inspiration and give you some hope, because let's face it, we all need a little hope in this world. So we're going to talk about using less energy and taking CO2 out of the sky. And this is in the form of a student challenge that I run when I teach an energy course at Georgia Tech. I'm doing it right now at Georgia Tech. My students are competing in the Carbon Reduction Challenge. And I tell them, go out and don't just make a plan to reduce carbon, get it done. You have 2 months. The clock starts now. Come back to me April 30th. We'll count it up. We'll see how much carbon you all reduced, and I'll declare a winner. Okay? Now, I started doing this. I had very modest goals. I said, oh, I'll try to do like 1,000 pounds, you know. Now, we're looking at a class total of about 400,000 pounds of carbon dioxide reduced. 2 months. 24 students, okay? This is, to me, really illustrates the power of scale and passion. This is what we've done over the years I've been teaching this class. So this graph is illustrating the reductions achieved in this class since 2007. 2013 was my record, obviously, at 300,000 pounds. And this year, we're on track for over 400,000 pounds. They always do a lot of last-minute stuff to try to win, so maybe it'll be even better. I look forward to seeing the presentations next week. But this is saving money. We're using less energy, and we are saving the planet. And we are training the next generation to be proactive in this space, to get out there and do something. So it's all win-win. It's extremely fun. The blue line on that graph, I should note, is the average American's annual carbon dioxide footprint. So in case you don't understand what 400,000 pounds is, now you do. Those are many Americans' annual carbon footprints that these students are offsetting in this class project. This is extremely powerful. In fact, I have a carbon neutral person now, thanks to this class, so I take all the credit for their effort, like any good professor. So what do they get? Why do they do this? First, they want to help. I am inspired by these students. They want to help. It's their generation that's going to ride us out of this problem, trust me. And if your students are in here, I'm looking at you. I take them to DC to meet with lawmakers on Capitol Hill. They love it. I'm not sure the lawmakers love it, but I get a kick out of it, trotting them around to the same old faces and shaking hands and bringing our message about energy efficiency to Capitol Hill. And they also have a prize, which this year is courtesy of the Honors College at the University of Pittsburgh. So I usually never accept honorariums. I'm taking this honorarium and actually making it a cash prize for my students in the class. So thank you very much. They're very excited about that. This is the first year they have a cash prize on the line, so it really works. Students, we need students to fill this whole space out. People think, how can I contribute? I'm not a tree hugger. I'm not a tree hugger. We need climate scientists, which is what I specialize in. We need public policy experts. We need engineering geeks. We need economists who can run those kind of models. We need to understand our future in the context of present choices. And we need entrepreneurs to go out there and find a way to make all this money that somebody will make to solve this problem, students. So, oh, how did that get on there? Oh, well. Come to Georgia Tech, help us be part of the solution, And if you want to click that link, that'll take you to our department where we're tackling the climate science piece of this. This is personal for me. I've worked at these sites for 15 years. I fall in love with these sites. They're all no more than 2 or 3 meters above sea level. So these sites where these powerful climate records are coming from are going to be underwater. I would call it virtually certain as a climate scientist, which is IPCC lingo for 99% sure. Virtually certain, unless we make extremely aggressive actions within the next 30-ish years, it's certain that these sites will be underwater. So this is personal for me. This is why I'm here. This is why I go give a bunch of climate science talks all the time. And this is why I seek to inspire folks like you guys to engage however you can in this space. So the corals have spoken. Thank you for listening.